dig into the nitty gritty. Let's calculate. We're not going to be able to calculate a wave function for a molecule, but we can have an idea of what it looks like. We're going to come up. Basically, we're going to kind of half quantitatively do things. This isn't going to be I'm not going to quantitatively discuss molecules. We just don't really have the ability to do that or the time to really dig deep into it to be able to do answer quantitative questions. But the really nice thing is that we can tackle molecules in a qualitative way and then bring in numbers when we need to. So today I kind of want to dig into some math, but just what I mean by quantitative, I mean like get an actual number out. We can play around with wave functions and add atoms and subtract atoms from each other to come up with new. For wave functions for molecules, this linear combination approach that we talked about last class. But and we'll eventually make this more complicated and start building things in. And I'll show you some examples. We'll use the computer to actually calculate things for us, and I'll show you some results. So every molecule that we'll talk about in this class, every type of molecule that we care about, we can just type into a computer and have it calculated for us. So we can at least confirm that our qualitative ideas are correct, which we'll find they are. So let's remind you a little bit about the approach that we're going to do. So what we want to do is, our goal here is to construct wave functions. I didn't spell construct right, or constructure. Construct wave functions for molecules. There's another way to write that. Of course, we might not even care about the wave functions. We might just care about the energies. Right? So equivalently, we could also say that calculate energies or properties for molecules, right? Again, if we know the wave function for a molecule or any system, we can calculate anything we want about it. Right? We just have to take an integral over the wave functions of whatever we want to calculate. So, of course, energy is the natural choice. But maybe we want to calculate something else, and we can certainly do that. But again, what we need is a wave function in order to do that. And the way we're going to do it, again, is through this technique, which is the linear combinations of atomic orbitals. And I'll go through, we'll work through the math for a very simple molecule. We'll do H2, right? And we'll look at H2 and also H2 plus hydrogen with 1 electron to the 2. To illustrate this approach, which I will call from now LCAO, to illustrate LCAO, and H is a really good example because they're the same atom. When we add two hydrogen atoms together, the math will work out very nicely. And then, but it's a completely general approach. We can do it for any molecule. It's just much easier for hydrogen. And the idea is very simple. Let's assume we have a molecule with n atoms, and the n sub I atom has n sub E, let's do this, n sub I, how am I going to write this? M sub I electrons. All right, that's better. All right, so for atom 1, it has m sub 1 electrons. Right? So for hydrogen, that's 1. Right? Carbon, it's 6, and so on and so forth. Okay? And what we're going to do is we're going to take for each atom, write its wave function as a sum of hydrogen-like wave functions. Right? As we saw, for atoms heavier or bigger than hydrogen, we can't solve the Schrodinger equation for them. So what we're going to do is we're going to take a base level, if you will, of things that we know, which are hydrogen-like wave functions. And we're going to create a new wave function for a given atom by making it as a sum of hydrogen orbitals. So for instance, well, let me write for the atom orbitals. All right, phi, this is the atomic orbital for some atom n sub I. Actually, I'll write this as phi sub I. So this is the orbital for the ith atom. It's going to be a sum from, let's say, j equals 1 to some number. It doesn't matter. It just depends on how many we want to add. We'll just do a sum of a hydrogen wave function. Right, so this is a hydrogen-like wave function. It could be the 1s or the 2s, anything you want. So I'll call it IH, or J rather. Sum over J. And then we have to multiply it by some coefficient, C sub J. Just a number, okay? And we set this up so that the sum of all the C's squared is equal to 1. All right, so the idea is we're just normalizing it, right? That you have you're representing your atom I as some sum of wave functions that are hydrogen-like, and the total contribution of them should sum up to 1. And so some of them might be less than 1, some may be close to 0. You know, we don't know. Right? Depends on the atom. Right? These are just numbers, coefficients, real numbers. All right, we'll see this very clearly with an example. Okay? So now we have a wave function for each of our atoms that's represented by a series of hydrogen wave functions. Could be 1s, 2s. Depends on what we want to represent. We'll make a choice every time we construct a molecule what we want to represent our system as. And then what we're going to do is construct the molecule, construct the molecular wave function by summing over all the atomic wave functions. We'll call the molecular wave function big psi, like that, by LCAO-MO, right? We're going to linearly combine atomic orbitals. So psi, big psi, is going to be equal to a sum from I equals 1 to n, where n's the number of atoms, times some new coefficient ci. Let's just call it d, just to keep it consistent, some number d, times the atomic orbital for that atom. Okay, so we have two layers of approximation. We don't know what the atoms look like, so we're going to approximate it as a sum of hydrogens. Maybe there's a little bit of 1s character, 2p. We'll look at this as we go through atoms. Right? We'll do a calculation every molecule we talk about, and we'll see how this works out. And then I'm going to create the molecule wave function by adding the atoms together. Okay. Pretty straightforward. All right. Of course, the math is more complicated, but the idea is very simple, right? We're going to guess our atoms by basically making it a sum of hydrogens and then make our molecule full of these hydrogen-like atoms, summing over all of them. So let's work out the math for this a little bit. So we have this new wave function here. We can write all these out. We can put the 1s orbital in here. Right? Since our atomic orbitals are made up of wave functions that we know the function for, right? We know what these look like, then that means our molecular wave function is a function of things that we understand that we can write down. Because these are effectively, you're summing over a sum of things that you know. So we have this big wave function. Psi. And what do we want to do with it? Well, we want to solve the Schrodinger equation for it. Right, we got to apply the Hamiltonian to it and get the energy back times the wave function. All right, we want to solve this. But we don't really know what the Hamiltonian looks like. We might not even be able to solve this exactly, right? This is not always solvable. I'll call that rarely solvable in this form. Right, so we have to come up with a different approach to solve the Schrodinger equation. And the idea is actually quite simple. What we're going to do is, from the midterm, apply the variation method, which says that the energy, the guess energy of your system, so it's the energy of that molecular wave function we guess, is the integral of the wave function times the Hamiltonian times the wave function, d tau, whatever that is, across the entire space, divided by the integral of the wave function itself. Right, this is problem 3, I think. Right, so instead of solving this differential equation, all this complicated stuff that we do, we're just going to We know what the Hamiltonian looks like, we can write it down. That's what we did in last class. We wrote it down for the hydrogen molecule. So we're just going to make a guess for our wave function that we've constructed and guess the energy, right, which we use with this formula. So this is a guess for our energy. Okay. So what I'm going to do is I'm going to use the same approach, and now I'm going to apply it to this equation. Right? So I'm going to write this out in a little bit broader detail. Okay. What I'm going to do is I'm going to multiply both sides of this equation by psi integral. Right, multiply both sides. I need to add an integration variable, but it doesn't matter, just for safe right now. And so so we have the integral of the Hamiltonian, right? This is the expectation value of energy equals, E is just a number, so that comes out. Psi star, psi squared. So we have that the integral of the Hamiltonian, right? This is the energy of the system is equal to the energy times the overlap. Right, this wave function here, psi star psi. All right, but psi is a combination. Right, we need to break this down a little more because again, our wave function is actually a sum of smaller wave functions. So in fact, what this looks like, let's say for instance that, just for example, we represent it like this. Okay, just two terms, just for example. We can have as many as we want, but let's just do it for two for now. All right, and so we can plug that into this equation here. Sorry. These are atomic orbitals. Here I'm just plugging them in. So we can FOIL this out. Right? We can FOIL it out. And what we're going to find is that there are going to be some terms proportional to the integral of theta 1, theta 1. Right, the Hamiltonian in the middle. There might be some terms that look like theta 1, h bar, theta 2. Right, when we FOIL this all out, FOIL the left side out, left-hand side, we're going to have terms that look like that, right? All the different combinations of all the indices. And the last one is theta 2, h bar, theta 2. All right, we have combinations, right? When we do the FOILing, we're going to get some integrals that have one atomic orbital on top of each other, two indices, the mixed ones, and then ones that are the same. All right, and of course it's the same on the same side. All right, so what I'm going to do is define a few things. All right, so we're going to have all these different terms on one side of the equation, similar terms on the other side of the equation. And I'm going to define two things. Define the number hij, it's got two indices, I and j, as the integral of phi I, h bar, phi j, tau. Right? And then Sij is the integral of phi I, phi j, tau. That's the right-hand side. Like that. Okay? And what we get from this is an equation that says that hij psi is equal to E times Sij psi. Like that. Or psi is some wave function. All right, I'm just keeping it general here. Maybe I could write like this instead. Let's do that. That's better. Okay, so we have this number here that has two indices that depends on which integral you're taking, and it's going to be equal to the energy of the system times the overlap, which is the right-hand side integral, psi squared. And you get the wave function out on the other side. So now what I want to do is I want to change our viewpoint a little bit. Right, that equation still doesn't really help us do anything. But instead, let's change our perspective a little bit. What I'm going to do is instead write my wave function as a vector, which is just the coefficients on the outside. Remember that psi here is equal to C1 phi 1 plus C2 phi 2. These are atomic orbitals. Okay, so instead of writing phi's out, I'm just going to represent the coefficients, right, on the outside. All right, these are implicit. All right, I know that maybe this is a 1s orbital, and this is a 1s orbital for the other atom. And that's implicit here. My vector is now, my wave function is now a vector, C1, C2, which is again equivalent to C1 times phi 1 plus C2 phi 2. Right, you can think of the phi's as the directions, right? When you write a vector in x, y, z space, you have implicit that the first coefficient is that times x. This is the y coefficient of the y part of the vector, and so on. Right, here what I'm going to use instead of directions, I'm just going to use the functions, these atoms. Right? So psi is just a vector of two components. How much of it is in phi 1, how much is in phi 2? Okay, when you write your wave function like a vector now, what that means is that Hij is a matrix, H11, H12, H21, H22. Which again, these are the integrals. Remember, each of these are the integral of that atomic orbital times the Hamiltonian times the other one where the other index is. Right? So for instance, H11 is the integral of phi 1 H, phi 2, or phi 1, sorry, d tau. Right? H12 is the integral of phi 1 H, phi 2 tau, and so on and so forth. Right? So we can write them all down. Right, again, depending on how many atoms I choose. Right now, I'm only choosing 2 atoms. Right, this is the wave function of atom 1. And this is the wave function for atom 2. Right, this is a 2-molecule system, so the size of this matrix depends on how big your molecule is. It's n by n. Right, so if you have n atoms, you have an n by n matrix. And then you have another matrix Sij, which is just the overlaps of all of these wave functions. How much does the wave function of atom 1 overlap with itself or with the other one, and so on and so forth. Right, so when I plug these matrices into the Schrodinger equation, what I have now is H11, H12, sorry, right, that's 2-1, H12, H22, and this is the Hamiltonian. Now we have psi in the Schrodinger equation, and that's represented as C1, C2. And that's going to be equal to the energy, H psi equals E psi, times the overlap matrix, times C1, C2. Right, so this is E here, this is E, and this whole thing right here is psi. Okay, so all I've done is I've casted my integral, my Schrodinger equation into a matrix form with vectors, where I represent the wave function as a vector associated with each of the atoms. Each component is the coefficient on the outside of the wave function for that atom. All right, so let's look at a simple example and apply this and see if we can solve this. So the example I'm going to use is H2 plus. Okay, so I'm going to take hydrogen. So we have a hydrogen here, call it A hydrogen here, B, and then they share an electron. All right, the reason why I'm going to do H2 plus is because there's only one electron. We don't have to worry about electron-electron repulsion, which is the hard part of this equation. We just have one electron. All right, so how do I want to represent this molecule in terms of its atom atomic wave function? So let's call psi H2. All right, what is our guess for the wave function of this molecule? Well, let's keep it simple, right? Let's form this molecule from H1s, so from a hydrogen atom in the 1s orbital, 1s state, the ground state. Let's do 2x, right? Two of them, and then remove an electron. Right. Another way to think of it maybe is to add a hydrogen and a proton together. It's a reasonable way to think of it, but it doesn't matter which way we do it. Let's just take two hydrogens and just pluck an electron off. Okay? So the wave functions for each of these atoms, phi A, is just the 1s state, 1s wave function. Okay? And phi B here is the 1s wave function. All right, so that wave function looks like e to the minus r times a constant. And so the way I'm going to write the wave function for H2 plus is I'm just going to add these together. I'm going to write C1 phi 1 plus C2 phi 2. Like that. Right? Instead of, I'm going to just write 1 and 2 instead of A and B, just to keep it consistent. Right, so the way I'm going to represent this molecule is I'm going to add my two atomic orbitals together that my system starts in, the 1s orbitals. And I'm going to add them together. All right? Remember, this one is localized. One of them is at position 2. Right? We'll call that R2. That's at this position, and this is at R1. Right? So they're separated from each other at some distance. We'll call that distance R. Like that. Okay? So the way that we write this wave function in terms of a vector is just C1, C2. Okay? So when I write down this wave, when I write down the Schrodinger equation, I'm going to have the integral of, I'll write it nice and big here. So H matrix is going to be H11, which is the integral of psi 1s, H bar psi 1s, d tau. The next term is going to be psi, this is an A, we'll call this 1 and 2, psi 1s 1, H bar, oh sorry, this is psi 1s 1, 1. They're both the same. 1s2. This integral on the bottom left is going to be psi 1s comma 2. That's the 1s orbital on position 2 times H bar psi 1s 1. And then the one on the bottom right diagonal is 1s2 H bar psi 1s2. Yeah? We can evaluate this in just a second. And this is going to be equal to, again, we multiply this by C1, C2. And that's going to be equal to the energy of the system. We don't know that energy yet. Times the integral of psi 1s 1, psi 1s 1, psi 1s 1, psi 1s 2, psi 1s 2, psi 1s 1. This is the overlap. psi squared. Okay. So now we have to evaluate all these little integrals to get a nice formula, and we can do that. We're not going to do it here, but let's just kind of, we can simplify as much as we can. One thing to note, remember that the integral of psi squared is 1 for any psi. So this is 1, and this is 1. Okay, so we can simplify that so they're 1. And now we have these integrals here that are the overlap of the wave function centered at atom 1 times the wave function centered at 2. Right? So these integrals are going to be less than 1, but greater than or equal to 0. And these are symmetric. They're the same. If you think about it, if you just flip them, it's the same thing. So this one is equal to this one, and they're going to be some value between 1 and 0. Right? The reason why they're not 1 is because it depends on the distance. If this is position atom 2 and this is atom 1, then the wave function for atom 2 looks like this. Let me simplify that a little bit, sorry. That's atom 2's wave function. So this is psi 2. And psi 1 looks like this, psi 1. And so there's a region in the middle where they overlap, but not the entire function overlaps, right? If they perfectly overlap, then they're the same wave function and their integral is 1. So if this was right on top of this one, they would be 1. But it's obviously not 0 because there's some region where when you multiply them together, you have some area under the curve. Right? So that means that they're less than 1 but greater than 0. So one thing that we could write, for instance, here, is that we could write this as 1, 1, and some number a. Right? We don't know what it is, the overlap, but it's an a. It's just a number. Right? We can calculate it, right? If we fix r, we can write out the wave functions and calculate the integral ourselves and calculate what this value is as a function of r. Maybe I'll write it as a function of r, distance. Okay. Now, what about these over here? Well, if we look at this integral, for instance, in the Hamiltonian, this is the integral of the Hamiltonian times the psi 1s, the energy of the psi, this is basically the energy of the 1s orbital. Right? If you think about it, the Hamiltonian applies to psi 1s. So that's going to be the integral of psi 1s times the energy of the 1s orbital times psi 1s, which is E1s integral psi squared, which is E1s. Right, so this right here, this integral is the energy of the 1s orbital. This one, of course, is the same, because again, it's just located at a different position, but it's the same state, still 1s. And then we have these numbers here that we don't really quite know what to do with. Right, again, these are going to be dependent on, right, this is going to be equal to the energy of the 1s state times the integral of psi located at position 2 times psi position at 1. Right? And that's going to be a position-dependent thing. Right? So maybe we'll write these off-diagonal elements as alpha, and they're a function of r. Okay? So our total formula our equation for the Schrodinger equation looks like this. E1s alpha, which is a function of r, E1s, C1, C2 is equal to the energy times 1, 1, what did I write? A of r, times C1, C2. Like that. All right, so I'm doing a lot of math here. But we can immediately solve this as a solution, right? If you've taken, maybe you haven't taken linear algebra yet, but this is the same, this equation here Let me make sure I have it right. Yeah. So this equation here, I'll rewrite it one more time. E1s, alpha, alpha, C1, C2, so the energy of the molecule times 1, 1, what did I write? A, C1, C2. We can solve, this is just a solution of linear equations. It's just a set of linear equations that says that, for instance, that E1s times C1 plus alpha C2 is equal to E molecule times C1 plus AC2. So that equation, and then alpha C1 plus E1s C2 is equal to E mole AC1 plus C2. All right, this is, so what this, all this is just a series of equations, the functions, right? So this function, this set of matrices and vectors multiplied all together is literally saying the same thing as this, that this combination equals this plus this combination equals this. You have to set two equations. So two linear equations. Right? And so we can solve that. And the way that we solve this is we're going to take this and put it on the other side. So I'll write it instead as H C1 C2 equals E S C1 C2. We can write that as H minus ES times C1 C2. All I've done is factor out the vector is equal to 0. All right, so if I take the Hamiltonian matrix and subtract the energy of the system times the overlap, multiplied by the vector, what I'm solving is for the 0 of this function. What are the C1s and C2s such that, right? What are the coefficients C1, C2, and energy E that satisfy this equation? Again, I'm just doing algebra, right? All I've done now is that we have now in solving this equation by adding into a set of linear, right? We did this linear combination of orbitals. We've taken the Hamiltonian with the Schrodinger equation, and if we've separated our system into n atomic orbitals, then we have what it turned the Schrodinger equation is just a set of n linear equations that you can solve. Right? So I'll just write that out. Schrodinger equation for LCAO is just a set of n linear equations for n atoms. Okay. So we need a little bit of linear algebra to solve this problem, and luckily Wolfram Alpha will do it for us just fine. We can do, luckily for 2x2 matrices, we can do it on the board. It's really easy. So let me show you how that math works out. So we have H minus ES C1, C2 is equal to 0. So what that's going to look like is H11, H12, H21, oh, sorry, this is H21, I apologize. H12, H22, minus E1, 0, 0, E2. It's the energies of the orbitals. Times the overlap. that whole equation, times the vector C1, C2, and that's all equal to 0. Now what I can do is just a little bit of matrix math and put these together into one matrix. We have a 2 by 2 matrix subtracting by a 2 by 2 matrix, which means we can combine them together. So this is equal to H11 minus E1 S11, H21, H12, H12, E2, S22. It's equal to 0. So what we need to do is find, I missed the C1, C2, sorry. So what we need to do is find values C1 and C2 and E1 and E2. These are the things we're solving for. That one's dead too. What we need to do is find values for these numbers such that this is satisfied. And what you can find, and so what we're going to do in order to solve this, we take what's called a determinant of the matrix. Right, so the determinant, so for a 2 by 2 matrix, A, B, C, D, the determinant of A, B, C, D, which in this case is equal to 0, is equal to AD minus BC. Right? You take the diagonals and subtract them off of each other. This and then this. Cross product, if you will. And so what we need to solve then for this equation is the determinant of H11 minus E1 S11, H21 minus minus S21, H212 minus S12, H22 minus E2 S22 equals 0. Okay, and so all we have to do is just take the product of the crosses and then subtract them off of each other. So we're going to get an equation that looks like H11 minus E1 S11 times H22 minus E2 S22 minus this product, H21 minus S21 times H12 minus S12 equals 0. And when you do this, you get an equation that is proportional to E squared. Boil that out and set it equal to 0. And let me find my answer here. This is not the expression I wanted, I'm sorry. What you get is that the energy of the new orbitals, so these are now the energies of psi, and they're going to be equal to H11, which is the energy of the 1s orbital, plus or minus. Let me think about what this number is off the top of my head. H12 over 1 plus or minus s. Or this is the overlap This is the overlap of the two wave functions. So basically the idea is that so this is again the energies of your wave functions that come out. This is the molecular energies. It's going to be the energy of the hydrogen orbital plus or minus some term that talks about how much the two atoms talk to each other. Right? These are proportional to the integrals of the two wave functions centered in each of the atoms, the two 1s orbitals. How much do they talk to each other? So the more they talk to each other, the more the energy moves away from the H1s energy, the energy of the 1s orbital. So let me show you how this works. One of the things that you might notice is that because this is a function, this solution here, and I'll show you a way to do it on Wolfram alpha that makes this super easy once we in the next day or two, next class, is that this integral, my fucking pens are dying today, that this is an equation of E squared. So there's two solutions. Right? So what that means is that in fact the system, that what it predicts is in fact there are two states of two different energies, the plus and the minus combination, depending on which solution of this equation you take. And this is kind of one of the key points of LCAO theory, is that by combining in atomic orbitals, which here we combine two, you get in so-called molecular orbitals or molecular wave functions out. So for H2, our guess is 1sa plus 1sb, right? An S at the A atom and one at the B atom, or one or two, however you want to think about it. This is two atomic orbitals. And therefore, H2 has two molecular orbitals corresponding to energies E plus and E minus. All right, I'll draw a diagram of this to show you what it looks like. So let me show you in terms of energy. Let me just draw an energy diagram to show you what happens here. So what I do now, I'm going to draw here in terms of, let's just call this position and energy. There's not really a point in calling it position. And then what I'm going to do is I'm going to mark where the 1s orbitals are. Right? That's where we start. So let's call this A. This is atom B. And let's say this is where the energy of the 1s orbital of hydrogen is. So this is 1s, right? So we have two 1s orbitals that are at this energy. Okay. It doesn't matter what energy they are. They're just at some energy. We'll call it E1s. So when we combine these two orbitals together and solve this equation, what we get are two new orbitals that have new energies, which are E1s plus or minus this term here. Okay, so we take one, we take the plus, so there's going to be one that has higher energy than E1s and one that's lower, because there's a minus sign here. All right, so when we combine the orbitals together, H2 now has an orbital here. We'll call that psi 1, or psi plus, or psi minus, sorry. And then there's a new one that's formed of higher energy, psi plus. Like that. Okay, right, so what we've done now is when we've combined our atoms together, we create two new orbitals, one that's lower in energy and one that's higher in energy. Right? And the difference between, the splitting between these is 1/2 this difference, which is H12 over 1 plus S12. Oh, no, it's not. It's just H12 minus S12, sorry. And this difference is H12 minus 1 plus S12. So what we've done now is our wave functions for our molecule, right? This is H2 plus here. We formed two new orbitals, two new states where the molecule can be in. One that's in lower energy than what the atoms provide us, and one that's higher in energy than what the atoms provide us. Right. So if we wanted to fill this with electrons, so for let's just do H2. H2, we start with one electron in each position. Right? And when we combine, those electrons are going to have to go into a new orbital. They're going to have to go into the molecule. And of course, electrons want to fill the lowest energy shell. So we would predict that our electrons would fall into this orbital here, this lower energy one. Right? So what we've done now is we've taken two hydrogens with one electron, we've put them together, created a new wave function that we can now store two electrons in. Okay, now the question is, what do these look like? Right, what do these wave functions actually look like? So what are the identities of our new molecular orbitals? Right, I won't go through the math, but you can do it in Wolfram Alpha, and I'll show you how to do that when we get to it next week. But I'll just tell you here that our new bonding orbital, this orbital that the electrons go into, call it psi minus, is equal to 1 over the square root of 2 times the wave function of the 1s orbital located at A plus the wave function at 1sb. Right, so it's a sum of the two hydrogen orbitals. Maybe it's more reasonable to call that plus. I'll just call it minus here, just to keep it consistent. And then the other one is going to be the difference of the orbitals. So in terms of vectors, this one is 1 over the square root of 2, 1 over the square root of 2. And this one is 1 over the square root of 2 minus 1 over the square root of 2. Those are our new vectors. Right? Those are our wave functions for our molecule. All we've done is we've combined two atomic orbitals together, two 1s orbitals together, to make two new orbitals that are molecular origin, and we get a sum and a difference. All right, what do these look like? Well, let's remember that the 1s orbital looks like a sphere, spherical. Right? And then on a plot of r versus psi squared, kind of looks like this, spherically symmetric, and it kind of has this lobe-like shape. And so what we're going to do is that, so psi plus, our bonding orbital, is psi 1s plus psi 1s, one at A and one at B. Right? And what is that going to look like? Well, we have an orbital that looks like this and an orbital that looks like this from our two atoms. We're going to add them together, right, which means that this region is going to get amplified. Right? And so if I were to draw it as two spheres, here's our two 1s orbitals for each of our atoms. I'm going to add them together, and they're going to share density together. They just add constructively. Right? So our resultant orbital looks like a big, long ellipsoid centered with lobes at A and B. Right now the electrons are shared between the atoms. Right? We call this bonding. Right? This is what's called a bonding orbital. Right? Remember that all bonding is, at least covalent in a covalent way, is the sharing of electrons across two atoms. Right? A constructive sharing. Right? And so when we add two 1s orbitals together constructively like this, Then we form a region that is of probability that is shared between the two molecules, this region where they overlap. And that's a bonding interaction, and that lowers our energy. Okay, so we call these bonding orbitals. Now what about the other one? Right? Again, it's good that the bonding orbital is in lower energy, right? If it were higher energy, then we would never have bonding. And so it makes sense that the bonding orbital is lower in energy. Now what about the other one? Well, this is going to be the difference. Okay, so if I were to plot the wave functions of this system, one will look like this, sort of, and the other one is negative, like that. Typically, the way that we draw these in terms of spheres is we have one that's shaded. We call this like the positive, if you will, and then we have a negative, which I'll just draw as clear, the negative side. And so what happens when we add them together? Well, when we add them together, regions where they don't overlap are going to be intense, have a lot of probability, and regions where they overlap, there's going to be little probability. Right? So in this case, we have a depletion of probability in the center. Right? So when we add these together, in fact, they add like this, where you have a lobe on the outside of atom A and a lobe outside of the atom B, where the electrons can exist, but they can't exist in the middle because the wave functions cancel each other out here. Wave functions destructively interfere in the center region, in the bonding region. Okay, so this is what we call an antibonding orbital. It's the opposite of a bonding orbital, right? Instead of having constructive overlap, where the electrons can be shared in between the atoms, the electrons want to be far away from each other in this orbital, right? Because there's no the probability between the atoms has been depleted significantly, and that leads them to want to be on the outsides instead. Okay. In general, when you add two orbitals like this, when you add two orbitals together, any two atomic orbitals together, you're going to get a bonding pair and an antibonding pair. But the bonding characteristic how bonding they are depends on that extra term, the H12 term plus 1 plus or minus S12 term, right? This tells you how well the orbitals spatially interact, or overlap or interact, however you want to think about it. So if you have two wave functions, two atomic states that you want to combine to form a bond, if they don't talk to each other at all, if they have no overlap between each other, they're not going to form a bond, right? They're going to form what we call a non-bonding orbital. It doesn't change the energy of it all, it just looks like an atomic orbital. But the more they bond, the larger this term becomes, which means we stabilize the bonding orbital that comes from this, and we destabilize the antibonding orbital that comes from this. All right, so for instance, if we had two atoms whose orbitals we add together that don't add at all, then this term right here, this additional term in the energy of the molecular orbitals will be 0. So that means that the energy doesn't change when you combine. All right, we'll see examples of this as we go through examples of molecular examples. We'll look through all sorts of different molecules, and we'll see that there are ways you can combine atomic orbitals to form very strong bonding to antibonding pairs like this. And there are going to be orbitals that don't interact at all, that don't form molecular orbitals. They just look like for instance, lone pairs, for instance. Lone pairs are a good example of a molecular orbital that doesn't interact or doesn't form a bonding pair. You just stick those orbitals, those electrons by themselves, they're stuck to that atom. And that's because they don't interact with any of the other orbitals in the atom. All right, we'll look at this as we go through the molecules. We'll look at H2O and methane and so on and so forth. And we'll see this. Okay, so, but anyway, the gist is very simple. I've got a lot of math, and again, I'll give you some examples as we go through this class, this section of this math. Eventually, we'll get to a method, approximation method called the Huckel method, where we'll be able to we'll do this all the time. And I'll show you how to do it, but I just kind of want to talk about it conceptually today. The idea is that you're going to add atomic orbitals, and if they overlap each other, if they can share probability of electrons, if they can share electrons, then they're going to form a bonding, anti-bonding pair like this, where our atomic orbitals look like a mix, an equal mix of, for H2 at least, an equal mix of both atoms, right? The sum of the atom orbitals or a difference in the atom orbitals. Let me prove to you that this is real. Any questions? Okay. So what I'm going to do today for the last 10 minutes or so is I'm going to have the computer calculate this for us. All right, and I'll show you that when we combine two hydrogens together, we're going to get a set of molecular orbitals out that look like a half sum of both, an equal sum of the left atom and the right atom. All right, so what I have here is I'm going to use a program called Psi, which is literally a program that solves the Schrodinger equation for molecules. Here's the input file. I won't go into too many details. So basically, I define the molecule, two H atoms that are separated by 7.75 angstroms. It's about the bond length of an H2 molecule. And what I'm going to do is calculate, I'm going to optimize the geometry. Basically, I'm going to minimize the energy with respect to the bond length. So I'm going to adjust the bond length until the energy is minimum. And then I'm going to solve the Schrodinger equation for it. And the important thing with these calculations is you have to choose a guess for your atomic orbitals, right? Remember that when we build these molecular orbitals, we add atoms together, but each atom we have to make a guess for. Right? In our guess, we used 1s orbitals. Right? We just said each hydrogen atom is represented by a 1s orbital. But we could add as many orbitals as we want. We could say each hydrogen is represented by 1s, 2s, 2p, 2d. We can add as many approximations as we want. And so I have to make a choice. And so what I'll do is, as we go through this, I'm going to keep adding more guesses to our atomic orbitals, right? Make our atomic guesses larger, and we'll see how the system changes as we do that. All right, so what I'm going to start with is the simplest. And let me define this word, because I'm going to use it a lot. The term that we use for the choice of atomic orbitals that we use is called a basis set, which is the set of atomic orbitals we use to construct a molecule. Okay? We can make it as small as we want or as big as we want. We can include an infinite number of orbitals. We can include just two, right? In our case, we just did two. Call that a minimal basis set. It's literally the smallest possible guess you can make, two 1s orbitals. But there's no reason we couldn't include more and more. All right, so let's do that and see what happens. So what I'm going to do first is I'm going to do it with what we call the minimal basis. So I'm going to I'm literally going to have the program add two 1s orbitals together for the hydrogens and calculate the molecular orbitals from there. So give me just a sec. Oops. So again, there's nothing fancy here. This is just a bunch of text. All right, so what I'm going to do is I'm going to submit my input file for hydrogen into my program, and it's going to solve the Schrodinger. It's going to adjust the bond length of hydrogen, the hydrogen molecule, and calculate the electronic energy at every point until it finds the bond length that minimizes the energy, the equilibrium bond length, and then it'll calculate the energy of the molecule at that position. And it's done. That's it. So let's look at some of the output from this. I'm just going to go to the bottom, and I'll write some numbers down. So right here are some numbers. There's a matrix, a 2x2 matrix of numbers there. So let me go ahead and write it down for you. So this matrix is 0.545, 0.546, excuse me, 0.546. And the other numbers are 1.25 and minus 1.25. All right, these actually tell us the coefficients on the orbitals, molecular orbitals. So this is molecular orbital 1, molecular orbital 2. This is hydrogen 1 and hydrogen 2. Okay, so our wave function, we have two wave functions for our molecule. We just read down the list. This is going to be 0.546 times the wave function for hydrogen 1, which I think I call phi most of the time, plus 0.546 by 2. Did I get that wrong? No, that's right. And then there's another one, which is 1.2551 minus 1.2552. And if we look at these, if we think about, and then we have to ask the question, well, what are these orbitals, these atomic orbitals that we're using here? And I have that list right here. It's just an s orbital. Right? So this is the list of all the basis functions we use. It's called STOVE 3G. It's a hydrogen atom with one electron. It uses an s orbital. It actually uses 3 functions for the s orbital, but that's okay. It's just one s orbital. It's just a 1s orbital, and we have a representation for it. So what this is saying is that the wave functions for this system is a sum of 1s orbitals and a difference of 1s orbitals. Now notice that the numbers are different, 1.25 and 0.54. Don't worry about that so much. They're not normalized. We can normalize them later if we want. The system outputs them not normalized. But the idea is that our bonding orbital, we think it's our bonding orbital, is a symmetric combination of our 1s states, atoms, and then the anti-bonding orbital is a difference of the two. Again, this is at A and B. These are different locations. Right? That's exactly what we predicted. Right? We predicted that we had a symmetric combination, positive combination for our bonding orbital, and a difference for our anti-bonding orbital. And let's double check that the energies are right? The bonding combination, the plus combination, should be lower energy. So let me scroll up just a little bit here and find the energies. Should be right here. Yep. So here are the molecular orbitals of our system. So here's MO1, MO2. MO1 is the symmetric combination of the two, and it has an energy of minus 0.59. Don't worry about the units of this. These are atomic units. These units are 0.5 is Hartree's is 0.5 Hartree's is 13.6 eV. It's the energy of the electron of the hydrogen atom. It's just an atomic unit that we use. So it has negative energy relative to the baseline, right? So that means that the 1s electrons, if you will, are at 0. The 1s states are at 0, and so this is stabilized by minus 0.6 units. And then our antibonding orbital is destabilized by 0.7. Okay? And that's exactly what we predicted. We predicted that the bonding orbital should be low energy, and the antibonding orbital should be high energy. And that's exactly what we see. You'll notice that these numbers aren't equal and opposite, like I predicted. But again, that's due to the fact that we're making some approximations here. Okay? Right? Very simple. Right? It's doing exactly the same math that I did on the board, but what it's doing is the hard part, which is calculating the integrals and all the different values, all the numerical stuff. But it does it in exactly the same way I wrote on the board. It constructs each atom as a sum of, in this case, 1s orbitals. Each hydrogen is a 1s orbital. We add them together, and we solve the Schrödinger equation for that combination. Right? We calculate all those little integrals, all those little matrix elements, all the different elements of the matrices, and solve the system of linear equations for the energies and the wave functions. Right? And of course, the computer does it in exactly 6 seconds. Right? Much faster than we can ever do it. Now, what the question is, so let me write down the energy of this system. And let's instead do a better calculation. Let's say, well, maybe this isn't really a best way to do it. So the final energy of this molecule is this number right here. Let me write it down. What I'm going to do is we're going to calculate this energy with a couple different methods. So the method here we'll call as minimal. So that's 1s plus 1s. And the program gives us an energy of, in atomic units, I'll call that AU, of minus, 1.1175. Okay, so what I'm going to do now is I'm going to make my guess better. What if instead I represent my system with 1s's and 2s's instead, and then add them like that, right? Add the 1s's together and add the 2s's together, just like we did for the minimal part. But I'm going to add a different set of orbitals, right? So now my wave function for hydrogen A is C1, the 1s orbital, plus C2, the 2s orbital. And our wave function for HB, the other hydrogen, is C3, we'll call it 1s, plus C4, 2s. Right? I'm just going to add more terms. Right? So I'll do that. The basis for that has a different name. And again, the names don't really matter so much. If you take computational chem, maybe you'll learn these, but they're not big. So what I'm doing is instead of having 2 orbitals, I have 4. Right? And I'm going to combine them all together. It's done. Now it's hard to emphasize this. I'll tell you a story when we get to larger molecules, but the fact that this only takes 5 seconds is an amazing feat. And when this theory was developed, just to do this simple calculation with two 1s orbitals on hydrogen, it would take a theorist almost an entire year to do it. We'll look at nitrogen, for instance. We'll do nitrogen with a simple basis set. Simple as basis we could do for a nitrogen molecule. The program will calculate in less than 10 seconds, which is a problem that took the person who came up with that calculation 3 years to do by hand. Right? So the computer is really it's really amazing how fast and efficient this is. Okay, so let's look. So now my basis set, if you notice, now has 2 s functions. It's got 2 s orbitals. They have different coefficients, but that's okay. But we have 2 s functions now. We're adding 2 s functions together. And here is our output, our wave functions here. So for our larger basis set, the bonding orbital, remember we put four atomic orbitals in, we get 4 out. Right? We have all these orbitals, and so our bonding combination, which is this one, the first one, is 0.29, 0.31, 0.29, and 0.31. And you can see the other ones are all different by a negative sign roughly, right? They have 2 negative signs combination for different ones. Right, so now what's happening now is that my wave function now takes a little bit of 1s character and a little bit of 2s character and puts them together into a combined wave function. Right? Takes a little bit of 1s and puts a little bit of 2s. All right, so now we've made our function bigger, more complicated. And let's look at the energies. Which are here somewhere. Yeah, final energy is minus 1.122. So now we do 1s plus 2s minus 1.122, right? Is that what it says, 122? Now it's slightly lower in energy. Right, we've gone from minus 1.17 to 1.12. That doesn't seem like a lot, but it's a lot in energy. Again, remember one EV, or sorry, 1 AU is on the order of 240,000 wave numbers or something like that. It's a really big number. So small fractions is a lot of energy. It's hundreds of kilojoules per mole difference. These numbers are just are just normalized to a weird value. So you've noticed as we make our predictions better and better and better, our energy gets lower. All right, so I only have like 1 minute left. So let's do something crazy. Instead, let's make our basis set huge. What happens? And again, the idea is that the more functions we put into our guess, the better it is. So what I'm going to do now is give it an absurd basis set. And let's look at how big this function is. It has 46 atomic orbitals. So you get 46 molecular orbitals. Right, you can see the coefficients, all 46 coefficients here. This is the bonding orbital, the lowest energy orbital. You can see that there's some contribution from some of these, but most of these are 0. Right? Again, you want to have a basis set that works for all of your atoms, so you build a basis set that works for everything. So if you have more than just hydrogen, chlorine, silicons, carbons, you might need all these basis functions. The p orbitals might play a role in the d's and stuff. So you have all of these numbers. And if we look at the size of the basis set, for hydrogen, it has 1s, 2s, 3s, 2p, 3d, It has 1s, 2s, 3s, 2p, 3p, 3d, 4s, 4p, and 4d. Right? So what we're doing is we're making each of our little atoms more and more like larger and larger sums of hydrogens. We're just approximating with more and more functions. And if you can, again, we're only looking at hydrogens right now, so it's not that important, but you can imagine when you're getting to chlorine and all these atoms that have lots of electrons, we'll see this, these might start playing a role. The P's and the D's and the higher energy S's and stuff, right? They might playing a role. Here they don't play that much. As you can see, most of the coefficients are on the first couple of atomic orbitals. That's like the 1s and the 2s and the 2p. And the energy for this system, if I can find it, is minus 1.133. Right? The energy is going lower and lower and lower. As our guess gets better, the energy decreases. So 48 functions give us this value. And in fact, if we went to infinite, we would get the exact number. I don't know what it is off the top of my head. But again, this is the variation theorem that was from the midterm. Remember, in the midterm I said that you can make a guess for what you think your wave function looks like. The better the guess, the closer the energy is to the exact energy of the system. But it's always greater than. Right? So the exact energy is the lower bound. And as we start to add more functions, we get a better and better guess for what our molecule looks like. And our energy decreases and starts to approach the exact limit. Okay, so if I had the ability to make an infinitely large basis set, I'd get the exact energy for H2. Right? But what I can do is I can say, well, what's my accuracy? If my accuracy is a kcal per mole or a kilojoule per mole, I want to be within a kilojoule, well, then I can figure out roughly how many functions I need to get to within a kilojoule of the exact value. Right? But all comes down to a guess. Right? How do we guess our functions? Right? And all the program's doing is just adding combinations of atomic orbitals, more and more and more of them, and then we basically have more ways to fit and parameterize our system, and that gives us a better guess. Right? And we're always guaranteed that we're going to approach the exact answer the more we put in. All right, so again, this is for H2. We're going to look at more complicated systems on Monday. But the same idea, the same principle is exactly the same in all of these cases. Okay. All right, guys. Have a nice weekend. I will have your exams back for you on Monday. You'll probably hear from me probably Saturday with an email with your midterm grades or whatever your grade so far is. And I'll return the exams on Monday, and we'll go over them if you'd like, or we can just throw them away and ignore them if you'd like to. Up to you. Have a good weekend, everybody.
Have a good day. You going off the site?
Yeah, you too. Thank you.
What program is that?
It's called Psi, like as in like Psi wave function Psi. It's a free program. Runs on Windows, Macs, and Linux.
Have a good one.
You too. Thank you.
I enjoy the buy developer beer.
What's that? Oh, buy developer beer. Yeah. Yeah, it's done for free out of the. It's a collaboration between Georgia Tech and Virginia Tech, and a couple other places. There's only one paid. I think there's only one paid employee for the company. Yeah. I'm not even sure she.